Data storage is not one size fits all. You either store information in rows, keeping entire records together, or in columns, grouping identical attributes across all records. Row-based storage is the engine of transactional systems, or OLTP. It excels when you need to quickly insert, update, or retrieve a single complete record, like a customer's profile or a specific order. Analytical systems, or OLAP, demand a different approach. When you need to aggregate millions of rows to calculate a total or an average, row-based storage forces the system to read unnecessary data, wasting precious I/O. Columnar storage solves this by physically separating attributes. If you only need to calculate the sum of sales, the system reads only the sales column, ignoring everything else entirely. Because columnar data groups identical types together, it is highly compressible. This reduces your storage footprint and accelerates query performance by minimizing the amount of data moving from disk to memory. We begin by preparing our environment. Using the app package manager, we install unzip and curl. These essential utilities allow us to download and extract compressed files directly from the command line, forming the foundation for our data processing workflow.
The package manager confirms the successful installation of unzip. Notice how the terminal reports the unpacking and configuration process, ensuring the utility is ready for use. With these dependencies now resolved and verified in our environment, we are prepared to handle compressed archives and proceed with our data processing tasks.
To get started with DuckDB, we first need to ensure that our system has the necessary tools for downloading and extracting files. I'm installing unzip and curl using the package manager, which will allow us to fetch the DuckDB CLI binary and prepare it for use. The package manager confirms that unzip is now successfully installed. By using the non-interactive flag, we bypass manual prompts, ensuring a seamless automated setup. This prepares our environment to handle compressed archives, which is a critical prerequisite for fetching and deploying the DuckDB binary in our next step. Next, we fetch the DuckDB command line interface. By using curl with the silent and follow redirect flags, we download the Linux binary directly from the official GitHub repository. This lightweight, high-performance analytical database is perfect for querying local files without needing a complex server setup. With the zip file downloaded, we extract the contents using unzip. Once the binary is available, we use the chmod command to grant it execute permissions. This step is crucial as it transforms the downloaded file into a runnable program that we can invoke directly from our terminal. Now we create a sample dataset. We use the printf command to generate a CSV file named sales.csv, containing product names, quantities, and prices. This structured text format is a standard way to represent tabular data, making it easily readable for our database engine. We can now query our CSV file directly using DuckDB. By passing a SQL command with the -c flag, we instruct the engine to read the file and display the contents. This demonstrates how DuckDB treats flat files like database tables, allowing for immediate, powerful analysis.
Finally, we perform an aggregation. We group the data by product and calculate the sum of quantities, sorting the results in descending order. This shows how quickly we can derive meaningful insights from raw data using standard SQL syntax, all within a simple terminal environment.
Notice the output table generated by DuckDB. The engine automatically infers the schema, assigning the varchar type to our product names and int64 to the numeric columns. This type safety ensures that our subsequent mathematical operations, like summing quantities, execute accurately against the parsed CSV data. Observe how DuckDB handles the aggregation results. The total QD column is automatically cast to an int128 type, providing high-precision arithmetic for our sum operation. This dynamic schema inference allows the engine to adapt to the data's scale, ensuring accurate calculations without requiring explicit manual type definitions beforehand.